Today, we have the pleasure of welcoming Dr. Gleb Belov from AMPL Optimization, who will be speaking to us about boosting business efficiency with AMPL and FICO Xpress. So I want to specifically thank Gleb for taking the time. It is 2 a.m. where he's connecting from. Gleb, thanks for being a warrior through this. Any questions, please direct them to the Q&A feature of the call so that we can ensure we get to them. In the chat, it's very easy for it to get lost. The session itself is thought of to be more of a workshop, and so you will have access to notebooks that you can follow along with. Those will be available in the following link that I've posted to the chat. In addition, to be able to run some of these, you will need access to a license. We'll provide a license UUID for you in the chat as well. So in a few minutes, someone will provide that so that you're able to run both AMPL and Express with its full features and no limitations. So without further ado, I leave the floor to Dr. Gleb Belov. Thank you, Gleb.
Hi and welcome. We'll start with an introduction of FICO Xpress, AMPL, and the AMPL Express solver connection, and then proceed to hands-on examples, which would be first a small mixed integer problem demonstrating AMPL high-level modeling and automatic tuning of Express parameters. Then a larger mixed integer problem and a nonlinear programming example looking at local optimality versus global optimality and starting points. FICO Xpress is a state-of-the-art solver targeting or featuring a breadth of reliable optimization algorithms on CPU and GPU. It has several parallel algorithms, including the rare case of dual simplex. It exposes advanced user controls via callbacks and settings, nonlinear programming functionalities, including the recent global solver and cross-platform determinism. Express has demonstrated consistent performance gains over recent years and is used in a variety of industries. AMPL is a modeling system. It was designed with the idea of a natural syntax. So if we look at the example on the left, first we have a small optimization problem in mathematical notation with some parameter sets and numeric parameters and decision variables x, objective function, and constraints. So AMPL syntax tries to stay close to that. Recent developments in AMPL include integration in Python and other programming languages, which gives tools for seamless deployment and data instruments. Also, it has automatic model reformulations that we're looking at below, and some tools such as IDE in Visual Studio Code, and quite recently, AMPL Bot. The workflow in AMPL features model and data separation. Your models, it can be one or several files, they stay in AMPL syntax, while data is provided from your preferred environment, which can be Python or some other programming languages, and the established data tools. So to look at the AMPL Xpress connection layer, we begin with automatic reformulations of some high-level constructs in AMPL. There are some logical and combinatorial ones, some nonlinear, and others which can be recognized implicitly. So logical and combinatorial expressions include things like implications and equivalences, if-then else, conjunctions, disjunctions, comparison operators, then counting, expressions, set membership, and piecewise linear. So ups, min, max are in fact piecewise linear functions. And breakpoint slopes is a more complex piecewise linear function. Complementarity constraint, and among nonlinear, there are typical nonlinear expressions used in optimization. And we have time to look at several examples how this is reformulated for Express. Let's start with a basic example, which would be an implication. Assume we have a binary variable, b, and an indicator constraint using that variable would state that whenever b is equal to 1, then we need certain inequality to hold. Such an indicator constraint is directly supported by Express. It is important to have tight bounds on the compared expression. For example, if you declare the variables, put the tightest bounds you know. And it is possible to set options which would linearize this indicator constraint, as you see below, which would give so-called big M constraint. This can be done in AMPL or in Express internally using either this or this option. Let's proceed to something more compound, a disjunction. Suppose we have a disjunction of two inequalities as here. To submit that to Express, we need three auxiliary binary variables. Two of them would be used as indicator variables into each of the inequalities. And the third one would be the result of the actual disjunction, which has the other binary variables as arguments. This is how Express would accept a disjunction. Again, the disjunction itself can be linearized using the option below. And if we go into the list of options in Express, this would be on the AMPL development page. So if you click on, if you just type dev AMPL.com solvers and then Express options, Express options, then we can search okay. This option we were talking about, it configures how the disjunction is accepted by the AMPL Express interface. And value 0 means that it is linearized, and 2, the default, means that is accepted natively and submitted to Express. And the next example is a count operator. suppose we have a constraint which assigns this variable to be equal to the number of times pattern P is scheduled in a certain sequence of slots in a scheduling problem. To submit this to Express, we need a set of auxiliary binary variables. So for each slot and each pattern, we introduce such a binary variable, and we add a constraint which is basically a unary encoding of this variable, of the index of pattern in each slot. For that, we need to impose the sum of the auxiliaries for all patterns equal to 1 for each slot, as well as this linear combination of the auxiliaries equal to the actual variable. And then we use these auxiliaries to compute the value of the original variable that we're interested in. This is just 3 examples, I think, just to give a taste of what happens. And then there is another layer in the interface which has more operational control of the actual Express solver. So full coverage of control parameters, then support of major Express features such as multiple objectives, multiple solutions, a warm starting, all types of mathematical programming problems that Express targets, continuous, mixed integer, nonlinear, infeasibility diagnosis, including irreducible inconsistent subsets, IAS, support of nonlinear formulas, and interface to callbacks. And now is time for hands-on, unless there are questions already. If we go to AMPL Collab, which is Collab AMPL.com, at least for those who want to run it at the same time, then we click on, so Collab AMPL.com, we click on tags, and at the bottom on Express. The first hands-on example would be a party scheduling problem. Let's open it in Google Colab, which would be to click this button. We can do it in a separate tab. So open in Colab and in separate tab. And we see this notebook. First cell in the notebook is meta information. So we have a scheduling problem for visitor host assignments. The model has no objective function, so this is a feasibility problem. Here we demonstrate high-level modeling, Python API, and automatic tuning in Express. The documentation references the interface layer documentation and the modeling guide. Then we have 2 initialization cells of Python code, which install necessary libraries and import the AMPL module. In particular, we need, so if whoever wants to run it, please paste the license ID here that is provided in the chat. And so basically now we can click run all just to execute the whole notebook. We start with the AMPL model for this. just one page. And the model should be clear from that. So we use the so-called cell magic, this one, to enter the model directly in the notebook cell. So when we start the cell with this, then the cell just gives AMPL statements. And for the model, we need a set of boats, and some of the boats are hosts, and the others are visitors. Then some numeric parameters which give capacity of each boat, the crew number, and their difference is the guest capacity. And we also need a set of time periods. So we would construct a schedule for all the time points. Decision variables H for each visitor and time point give the index of the host that is visited by the crew of the corresponding boat. And so the first constraint is the basic requirement that a visitor cannot visit another visitor. So what this basically says that the host index cannot be another visitor, such a disequality. This is one way to express it, which is the first example of a high-level constraint. The second constraint is that we want each crew to visit a given host at most once. And this can be expressed by null different. So among all the time periods, this visitor J always attends different hosts. Then subject to the guest capacity for each host and all time points. So the sum among the visitors that attend this host in this time point is less or equal guest capacity. And to find out if this visitor actually attends this host, we use an if-then expression, which gives us the crew capacity if that's true. And also, we would like any two crews to meet at most once. And this is the at most expression, which is a counting expression. So among all the time periods for a given pair of visitors, they have the same host at most once. So this was the model part. Now we define data in Python as Python variables. These would be lists of, for example, crew sizes and capacities, and again, a list of hosts. And then we assign them to the model parameters, which can be either, again, arrays, or which can be also a set of hosts. And B and T are actually Scala parameters. So after assigning all the data, the model is instantiated, and we can solve it. To use Express as the solver, we set in the following AMPL option. And to provide options to Express, we can use this option, and we run with default setting, except that we set a verbose login. We can use a snapshot feature this is a debug feature to save AMPL state, including the model, and call the solve method. When we run this, first we see some statistics on the reformulations. So the initial model that we receive from AMPL in the interface layer, it says it has some variables, some linear constraints, no objectives because we have a feasibility model, some count expressions, if-thens, conditional inequalities, and all difference. After the formulations, it has, well, some auxiliary variables, some extra linear constraints, and some indicators. This is all given to Express. It starts again with its own model statistics, continued relaxation, and then actual search begins. The search takes under 1 second, finding a feasible solution, and it says just one branching node for this small instance. What we normally should do after this, we should check for violations of numerical tolerances. Why is this important? Because mathematical programming solvers run with finite precision arithmetic. And so for larger instances, it is possible that some tolerance violations happen, especially if the solver applies scaling or if the model is numerically tough. So there are different ways to do this. First, we check the solve result. This is a variable in AMPL which says what's the return code, what's the status of the solve. We want it to be just optimal. And then we check the minimal slacks. This is for the variable bounds. This is for algebraic constraints. And this is for logical constraints. And this is the output. We can retrieve solution as a pandas data frame, which is efficient for large chunks of data. And now to demonstrate automatic tuning, let's first, why is tuning can be important? Let's again look at the list of options of the AMPL Express interface. So on this documentation page, it has about 600 options. Of them, about 500 are native options of the Express solver, and a big portion of them are relevant to solving efficiency. And for certain classes of models, some non-default settings can be best. And to find out improved settings for a model, well, it can be done by manual experimentation, but automatic tuning can be efficient as well. So to run automatic tuning, we first set this option. What it does, it switches off passing of the previous solution, which we have from the previous solve as an initial guess. So we want to run tuning without any known solution. And so by default, AMPL passes the previous solution to the next solve to enable iterative approaches, like local search. So we switch this off, and in the options for Express, we set this is to actually switch on tuning. Tuner method 1 is for MIP problems. Then we give 3 tuner threads, which means 3 tuning processes will be running in parallel. And for each such tuner threads, there will be 3 sub-threads for solving each current instance. And we leave it the maximal time and switch off tune history. So when we start this, we see that tuning starts with phase 1. In phase 1, it applies individual controls. So it tried to play with individual controls and find some promising ones. then at some point it starts phase 2, which is combining controls. And the final would be phase 3, which takes some promising combinations and removes certain controls from them in case they are redundant. And on this small instance, this all finishes up pretty fast with a certain combination of controls that was found to be best. In this run, it is this. For example, already the scaling parameter. Scaling is sometimes very sensitive, certain models to that. And others, for example, root select, heuristic search root select, and we can look it up in the option documentation what it means. And a certain bit vector control for local search heuristics. Certain values and some specific setting, 3, was found best for this instance. Now, the solve is run again. There's a final run of the solve with this combination of parameters. Which takes shorter time than the very first run. So yeah, this time, so whatever combination was found, if it improves the solving time, then it depends again on the instance and on the size of the instance. Let's proceed to the second notebook. This is another scheduling problem, paint shop color change scheduling. Again, let's open it in Google Colab. Open this button in a new tab. Paint shop color change scheduling. This will again demonstrate high-level modeling and this time manual solver tuning. The references cite a research paper which studies a large neighborhood search approach for a similar model. Again, whoever wants to run this notebook now, please, we need the license ID. And so short description of the problem is that just clicking on the contents for easy navigation. So paint shop color change scheduling problem. It is a sub-problem of a larger paint shop scheduling problem. And so color change scheduling is just looking at the decisions concerning coloring operations. So we're given some predefined sequence of skid types passing through coloring equipment, and we want to assign car parts to those skids. And we, in this subproblem, we minimized color change costs. And we will generate random data for this model. And some more details, model highlights. So we have predefined sequence of skid types, and each skid type can hold a one of a subset of predefined patterns of car parts. And each such pattern has a minimal and extra demands, how many times that it occurs in the schedule, and several kinds of color specifications. It has two simple colors, and they can be quickly changed between the skids. And it can have a maximal color. And there are three pieces of equipment which paint this maximal color. But whenever one piece changes the color, then it is disabled for 30 skids. That's the complication. And there is an objective function with some costs. So this is no more just a feasibility problem. This time, so probably we won't study all the details of the model, just an overview. We use the CellMagic write file to save the AMPL model in this file. So the model has, again, some parameter sets. It has some numeric parameters and variables. We can split them into primary and secondary, which is sometimes not unique. For example, the patterns that we assign to the slots and color max machine that we choose for each slot, but also secondary variables such as when a color change happens. And the first constraint is that we already know we compute a usage of each pattern using this high-level count expression. And then pattern use balance, for example, it's if we have any overuse or some missing count of a pattern, then to select the allowed type of pattern for each slot, we use a disjunction here. So according to the skid type, we only select the feasible patterns for this slot. And choosing a certain pattern implies that we select a certain color. Changing color means that we set the binary variable to 1, indicating this. Also, whenever we select a certain pattern, we need to choose a piece of equipment that is painting that color. And this is, again, with a disjunction. And whenever such a maximal color changes, so this expression, color max in slot S is unequal to color max in slot S plus 1. This implies that for certain waiting period, this piece of equipment is disabled, and we also need to set the flag variable, which is used then in the objective function to compute the costs. Just an overview. Then we have some Python code to generate random data for this model. We set 4 skid types, 5 patterns, and 50 slots. And some other parameters. We can study this data, some statistic properties, and run. We run with default settings, just limit the time just in case to 1 minute. Again, we can save a snapshot, which is a debug feature. This is a bit larger model. And when we look at the iteration log, we see that we have a best known solution in this column and a best bound. So we have an objective function in this model. And that means the solver provides us, well, when it has enough time to compute a best bound. And they both converge to the optimal value. So in just a few seconds, they converge to this objective function value. 4 seconds, 7,000 branching nodes. Again, we can check solution. If all tolerances are acceptable, so this time this is shown how we do it from Python. We can evaluate AMPL expressions in Python using this method. Again, we evaluate minimal slacks of variable bounds of algebraic constraints and logical constraint values. And the solve result, all printed here. Let's adjust some parameters and see if that improves the performance. Again, we don't want to reuse the previous solution in this experiment, so we set this option to 1. And for Express, we pass these 2 custom options. Let's look up, for example, what this one means. SB is strong branching. So this is an option controlling strong branching. It controls how the pseudo costs are used for strong branching, and values 1 to 6, obviously some internal parameters, which are not further detailed, but still can be played with. So when we set these values for these 2 options, then just as an example, we again have some best feasible solution and dual bound improving all the time. Yeah, we have a shorter runtime here, just 3 seconds something, and 6,000 branching nodes. And depending on the model and model kind and model size, the effect of certain parameters can be more or less. Again, we can retrieve solution as a pandas data frame. And yeah, if the time allows and many instances should be resolved of a certain class of models, then automatic tuning is recommended as in the previous notebook. Our last notebook is a nonlinear programming problem. Minimize the pairwise distance ratio for endpoints. Again, we start with a Colab page under tag Express. And this is the second notebook. We open it in Google Colab in a new tab. And again, if we want to run it, oh, no, take something different. Then we need to insert the license ID, which was posted in the chat. So again, I'll just hit run all. While it works, we step through. As an overview, what we want to show with this notebook is we consider the local and global optimizers in Express, which are different algorithms. The local optimizer is fast, but does not provide any optimality guarantee or even feasibility guarantee, while global optimizer can take more time, but with enough numerical precision, it provides dual bound, and it also finds a global optimum in given enough time. So we also look at starting points, importance of starting points, especially for local search. The model is rather short. We have n is the number of points that we look to allocate, and d is the dimension of the space. These parameters should be provided, or we construct the corresponding sets and declare decision variables x, which are bounded to the unit hypercube without loss of generality, and an extra variable t mean between 0 and 1, which would be the minimum squared distance of any 2 points. And then we have two sets of quadratic constraints. The first set does just that, so it sets t mean to be a lower bound on the squared Euclidean distance of any pair of points. And the other constraint bounds any such distance to be at most 1 without loss of generality, so we are in a unit sphere. And when we have this last upper bound, then actually minimizing the maximum ratio of distances equivalent to maximizing the minimum ratio. So our objective function is just maximize t mean, the minimum distance, minimum squared distance. So to instantiate the model, we set these two parameters n and d and run Express. To invoke a local solver, we need to set this option to 1. So by default, it's the global solver. We need a local. So we set this option. And to select Express SLP, we need this option set to 0. Again, snapshot as a debug feature. When we run it, we see several iterations which report they are converged, finishing with this objective value. So it's something like 10 to minus 5. Very short runtime, under 1 second. But let's explore that solution. So here is some Python code to print solved results, objective value, variable values, and do some plotting. The variable values look all very similar. When plotting, we see this is something like a two-dimensional shape, probably. And we suspect this is very far from the best. So what we can do, we can try a random starting point. So we just generate a random NumPy matrix of inside the unit cube. Here they are. We assign them to the x variables like this. And again, run the local solver. And here we see that the objective values are much better. So these two columns give some, I think this is estimate and this is a true objective value. Again, runtime is very short, 12 Barry iterations. Let's look at this solution. Now it looks like it has some distribution in 3 dimensions. Okay, is it optimal? We don't know. It was just a local algorithm. Let's solve with Express Global. And we would reuse the previous solution by default. So with default settings, Express Global is executed. We just set the time limit. Time limit 30 seconds. Now again, as this is an optimal algorithm, we see the best solution column for best solution values and for the best bound. And best bound is 1 because in our model, we provided this bound for the objective value variable. But it does not mean that the solver is comfortable at computing this bound, especially we see that it's not improving in this time limit. We explore that solution. It looks pretty similar to the previous one. So there is some improvement as an objective value, but we still wonder if that's optimal. And here is just a small exercise. Whoever wants to try this. So again, we're looking at the model. We see that this bound on the objective value variable, less or equal bound, is actually redundant due to the last group of constraints. So let's remove it. To do that, not here. We insert a new Python cell and we redeclare that variable. So we need an AMPL statement to redeclare. To evaluate an AMPL statement, we say ampl.eval and a string with an AMPL statement, which would be redeclare variable t min and just greater or equal 0, semicolon. And then we run the solver. Let's execute this with the same options. So 30 seconds time limit. But now it is a different model. And what we see here, again, we have a column for best feasible solutions and the best bound. Now, best bound starts with a worse value 2, but we see improvements straight away. And given enough time, these two would converge. So, but what we achieve in 30 seconds is there's still some gap. It says even the percentage of the gap. But we end up with a better objective value. And let's look at that solution. So we need to call this function display solution and the AMPL object as argument. Running this in a new Python cell. So let's execute. And this arrangement looks already quite symmetric. So probably they are evenly distributed on the unit sphere. We can suspect it is a globally optimal solution. Well, we still don't know, which depends on the model. So yes, that was an example for a nonlinear continuous optimization with local and global solver in Express. And final remarks. A tuner probably normally should be run on a set of instances to account for some diversity in the model class. Feel free to look at further resources on the websites. To continue trial, probably need to register on Humble portal and feel free to ask questions.
Great. Thank you, Gleb. Are there any questions from the audience here so far? Any other Australians like Gleb in the talk? No. Great session. Gleb, I have a question. So I see that there are a whole lot of modeling constructs, like logical constraints that are modeled in there. I see there's a not equal to. Is there by any chance a less than or a more than, greater than, but without the greater than or equal to or less than or equal to?
You mean strict inequality?
Strict inequalities, yes.
Well, this is very much a corner case. So even if we begin with indicator constraints, assume we have a strict inequality here, and if we know that the expression on the left is integer, then we can convert it to a less or equal -1. Right. But if this is a continuous expression, then generally we cannot do this, and so the user should either type less or equal whenever Actually, the exact value is known, but sometimes such comparisons arise during reformulations, and we have some parameters to control what epsilon value is used then.
Okay.
So if we look in the options, there is an option called this one. It's the option of the interface layer, tolerance for strict comparisons. That should be larger or equal to the solver's feasibility tolerance, which is internal express option.
Yep. Yeah, that makes sense. Thanks. Yeah, I was just thinking about in some cases where the feasible space is actually an open space, that less than that strict inequality is sometimes something people are interested in, but I agree. You can just deal with that with the tolerances.
Well, we cannot pass this to the solver. The solver can only accept non-strict inequalities in the indicator constraints.
Yeah, yeah. Any other questions? So Gleb, thank you so much for your time and for your talk and for connecting from down under in Australia. We appreciate your time and preparing all this material. To everyone, oh, sorry, there seems to be a question here. Is there any benchmarking between AMPL and other tools in compilation time?
Yes, there is some benchmarking. I don't know yet if I have it now. Ah, here it is.
Okay.
So I think AMPL is here the fastest. This is a 2023 paper, third-party benchmark.
Another question, could the solution pool feature help solving nonlinear problems somehow, finding nice starting points?
Well, solution pool is normally created during solving, and to pass, if the question is how to pass several initial guesses to express, we don't have an interface to that at the moment. So if someone is interested, then this can be added.
Yeah.
And
I'm
of course,
wondering,
also on the Express side, I mean, internally, of course, we do have some kind of solution pools, both to handle nonlinear solutions as well as, and also have them on the MIP side just to initialize different kind of heuristics, but of course also on the nonlinear side then to store solutions found from different heuristics. And then also, I mean, general, whenever we find any integer feasible solutions that are not nonlinear feasible, we will try to actually re-optimize them with SLP to find nonlinear feasible solutions. There, of course, we could also think about having additional solution pools to actually store different kinds of MIP solutions to start nonlinear from.
awesome. Any examples for constraints relaxation if we could not reach the optimal solution?
So this is probably about modeling and manual reformulation, how to make the model easier to solve if the original one is too hard. It is, well, the typical example is aggregation. We just take several constraints and add them up and hoping that the resulting constraint is, ideally it would become, for example, less dense. So numerical property improves and makes the model smaller. So yeah, creating some possibly redundant constraints, but which are easier, and replacing the original constraints by them or adding them separately can change the model behavior.
I mean, depending on how the optimal solution is meant, there is of course also the option of potentially adding slack variables and penalties to different constraints. If it's actually the difficulty is that you end up with an infeasibility, to try to find the least infeasible solution and maybe figure out which of the constraints you would have to relax to actually get valid solutions.
We have another question. Does AMPL have any infeasibility detector for any violations when the solver couldn't find any solution?
So
And we do have the IIS functionality for this, which is also supported from within AMPL. So that's typically, I mean, depends on what kind of problem you have, but like if you have an LP, I mean, it's generally supported for all different kinds of solves, so LPs, MIPS, and NLPs, where it would try to find a small subset of your original constraints that already proves infeasibility so that you can figure out a smaller subset to further investigate why it turns out to be infeasible.
Yeah, there's also the repair and feasibility tool as well from Express. I don't know if there's a interface to that with AMPL, but that will essentially add slack variables to these constraints, slack and excess variables to the constraints, and then solve that as well. So that's another method. I believe.
Yeah, I think.
Go ahead.
I think so. I think there is an interface to that.
Yeah, I think so too. How do you choose reformulations for Express? Is there any performance comparison to decide how to do it?
So in the 3 examples of reformulations here, which are pretty basic, there are actually quite a few others that are being done, and we do some benchmarking. So there are some differences. So there are some options how to do them, and we do some benchmarking to find the best for each solver is. This can depend if you have a nested expression, then how you redefine each layer. So yeah, there are some options to do this, and this can be solver dependent.
Okay. Awesome. Seems like we don't have any more questions, and we're at the top of the hour. Once again, I want to thank Gleb and the AMPL team, Jake, Ina, Meg, Tristan as well from the Express team for taking the time to put this together, put us in contact, and all the effort to coordinate with Gleb. Gleb, of course, biggest thanks to you connecting so late in Australia. Or so early, I should say. But we appreciate the effort, and this has been very insightful. So